Thanks to those that are here. This is always a hard time slot, Wednesday morning, last day of the conference, but have some really great sessions this morning and this afternoon. So my name's Sue Craig. I'm co-chair of the conference, and this is our second day of sustainability talks. Hopefully some of you caught some of the talks yesterday. There were some really good talks and discussions, and this morning's not going to be any different. So yeah, with that, I'm going to hand it over to Guy, who this morning's session, Yukon Needs in Mine Remediation and Restoration, and hope you enjoy the presentations.
Hello, hello. Thank you as well for being here. My name is Guillaume Nielsen. I'm a mine reclamation specialist with CoreGeo, a local environmental firm in town. I come from consulting, as it was my first job in the Yukon, and I did it after completing my PhD here in the Yukon as well, which brings me back to 2013. But prior to the current position I'm currently having, I served for 8 years as the NSERC Industrial Research Chair at Yukon University. And it's during that time that I started to attend and participate to this forum, the Geoscience Forum. And it's at that time as well that I realized that those big mining conferences, they are very good at presenting geology, business development, industrial updates, not so good to focus on environment. So I really tried for the last 5 years to bring environmental topics related to the mining world into the Geoscience Forum, and I'm grateful that the Geoscience Organization Committee gives us the opportunity to talk about environment, remediation, restoration, revegetation, and innovation. This morning we'll have the opportunity to hear about all of these topics with some projects that are making the difference by bringing knowledge where there is a knowledge gap. By offering a solution, sometimes even just the beginning of the solution, to a northern challenge. We will conclude the session with a panel discussion between researcher, consultant, and mining industrial rep that will discuss how they work together. I'll ask the presenter to stick to the 10 minutes time window that we have and encourage the audience to ask questions. It will be my duty to make sure we fit in the 5 minutes time window we have for questions. So to initiate this presentations series, as I said, as I served as the industrial research chair, I was working with the industry, the mining industry. I had at some point 7 industrial partners, 7 mines working together with me, and my job was to ask them, how can I support you? What are the environmental challenges that you're facing and I can help you with? 7 mines, 7 mining teams was challenging to work with sometimes, all in the same office. So we had different answers, but one answer was common. We need help, they said, we need help with revegetation. We need help to develop revegetation new technologies. And this is what the first talk is about. I'd like to introduce you to Ben Budze. Ben is a Master of Soil student at the University of Saskatchewan, supervised by Dr. Catherine Stewart. His research was based at Minto Mine in central Yukon, where he investigated the use of vertical structures as a revegetation strategy. His work supports northern reclamation practices by examining plant-soil interactions in overburden and identifying the key environmental drivers shaping early natural plant recolonization at Subarctic mine sites. Welcome, Ben.
Thanks for that introduction, Guillaume, and thanks to everybody for making it bright and first thing in the morning here. So I'm just going to dive right into it. If you have been following my research, I finally have some results that on the natural recolonization portion of my research that I'll be presenting on today because I find it to be the most interesting. I've titled my presentation, Vertical Structures as a Potential Revegetation Strategy for Accelerating Natural Plant Recolonization at Subarctic Mine Sites. So my experiment was conducted at Minto Mine, which is an open pit and subsurface copper gold mine located in central Yukon on Category A settlement land of the Selkirk First Nation. The site lies between Carmacks and Pelly, and the mine produced from 2007 to 2023. And this experiment started in 2021. So this is a map of central Yukon here, and you can see Minto Mine, top center frame. So unfortunately, many mine sites in the far north remain barren after closure due to extreme conditions for plant establishment and growth. This issue forms the premise of my research, which aims to facilitate the natural recolonization of native boreal plant species by addressing the severe physical-chemical properties of overburden and extreme environmental conditions presented by subarctic climates. So to guide this work, I've developed key principles that serve as a framework for my research. So the first is closure planning. In many jurisdictions, including the Yukon, mines are required to revegetate on overburden, and strategies must be included as part of their closure plans. However, very little research on the subject has been conducted at subarctic mine sites, and strategies used in southern regions, such as thick soil covers, are not always suitable. Since the Yukon was recently glaciated, topsoil is limited, making its harvest and storage for future application difficult and sometimes impractical. In addition, we also lack a commercial native seed bank, which restricts access to sufficient quantities of locally sourced seed. So these constraints emphasize the need to develop revegetation strategies tailored specifically to subarctic mine sites, rather than relying on methods designed for more temperate regions. So this is a photo of Minto Mine facing west over the site, and my project is located in the far back corner there. So subarctic mine site revegetation faces significant challenges related to both the soils and the climate. Overburden is a waste material generated during ore extraction and primarily consists of waste rock and mineral soil. It is typically coarse textured, low in plant available nutrients, and highly exposed. So these characteristics contribute to elevated surface temperatures, increased evaporation, and reduced water retention. Looking in those photos there, you can see that the overburden looks nothing like your garden soil. Climate further limits plant establishment. The growing season in the Yukon only lasts 3 to 4 months, and it's complemented with extreme temperatures and low precipitation. A key constraint shared by both the overburden and the climate is moisture availability. So growing season moisture availability in the Yukon is governed largely by snowpack, which determines the water supply as snowmelt infiltrates the soil. So given these constraints, strategies that enhance soil moisture may be critical in achieving effective revegetation in the Yukon. So back in 2021, an arrangement between Selkirk First Nation, Minto Metals, and Yukon University selected the mine's southwest waste dump as a suitable location to conduct the experiment. Overburden was spread to a depth of 30 centimeters across the site using mechanical site preparation techniques that created a surface contour. The overburden itself was characterized by a high proportion of rock fragments, coarse texture, low in organic matter. Some of our samples were contaminated with arsenic and copper, exceeded CCME guidelines, had a basic pH, was limited in plant available nutrients, and had high exposure to sun and wind. The site was also level with no slope and supported only minimal existing vegetation. So given these conditions, we anticipated that natural plant establishment would be difficult, so we chose to manipulate the physical environment as a strategy to accelerate recolonization. So this is a photo of the experimental blocks on our site. You can see our snow fences and hedgerows, which we use for our vertical structures. And in the bottom photo, you can also see the result of the mechanical site preparation there. So my experiment was a randomized complete block experiment with 4 experimental blocks ranged west to east across the site to account for potential environmental gradients. Each block has 4 structure types plus a control, and the structures were positioned perpendicular to the dominant wind direction so they could be more effective at capturing snow and blocking wind. So this is, in this photo here, the green lines represent our hedgerows. The orange lines represent our snow fences or abiotic structures, and then the blue lines represent our controls. So going into each of our structure types here, we have a tall snow fence, 65 centimeters in height, short snow fence, 35 centimeters. Our hedgerows, green alder, that averaged over 1 meter in height in our last year and had 100% survival. And then Dryas integrifolia here, entire leaf mountain avens. They also had a really high survival rate, but they didn't grow very high, about 6 centimeters. So to better understand site dynamics when we weren't there and to complement our field data, we installed time-lapse cameras. So these images shown here are overlooking blocks 1 and 2, and they capture our spring 2022 window and spring 2024 window. Spring melt conditions were noticeably delayed in 2022 compared to 2024. If you look at the dates, 2022 is in May, and then 2024 is still in April. And this difference may have been due to snowpack and how effectively our structures functioned. So in 2024, for example, more snow accumulated along the snow fences than in 2022. These images also highlight that because the site is level, meltwater naturally pooled in the depressions, which are indicated by these purple circles. These images here were taken during summer of the same years. So when comparing the spring and summer against each other, or when comparing the 2022 and 2024 summer windows, we see substantial growth of the alder hedgerows and natural recolonization across the site, so much so that the vegetation has nearly covered our control site in 2024. So this sets the stage for the next part of the analysis of how the structures actually influence natural recolonization. So what we did is we surveyed the natural regeneration at each of the structures across the site. So say this is our snow fence or hedgerow here. We used quadrats across 3 transects to survey the natural recolonization at distances 1 times the structure height in front of the structure, 1 times the structure height behind the structure, 3 times the structure height behind the structure, and 7 times structure height behind the structure. So before examining the effects of the structures, I first wanted to characterize the conditions across the site. To do this, I conducted a distance space redundancy analysis, which allowed me to explore the relationships between multiple environmental predictor variables and multiple response variables. So in this ordination, each point represents a specific surveyed plant community, and the colored ellipses illustrate how these communities are distributed across blocks 1 to 3. So overlaying on the ordination are 2 biplots, you'll notice. One is in bold, which is our environmental predictor variables, and then the gray, which are our species. So overall, we can see a lot of overlap in the ellipses, so the communities are quite similar across these 3 experimental blocks. So focusing on the biplots here, we see several significant environmental variables influencing community composition. Microclimate factors like volumetric water content, or soil moisture, you can think of it that way, and temperature were in fact strong drivers, which is important to note because those are the conditions that were included in our hypotheses with our vertical structures. And then when we break this ordination down into 2 parts, the right side is associated with higher rock content, higher temperatures, increased bulk density, greater sand content, and elevated calcium levels. Whereas the left side, in contrast, is characterized by high soil moisture, soil organic matter, and available nutrients, nitrogen, potassium, and phosphorus. So this creates a clear moisture nutrient gradient on the left and a textured temperature gradient on the right. So turning to the species biplots, the gray writing, many of the more desirable species are overlain or are associated with the higher moisture and nutrient conditions, particularly in blocks 1 and 2. Overall, while moisture and temperature are important drivers, the site's plant community patterns reflect the combined influence of multiple interacting soil and microclimate factors. So lots going on here. So during the natural recolonization, we also accounted for microtopography. So whether the species was on a microtopographic ridge or trough created by mechanical site preparation. So out of the 6 most common species we saw on site, only 3 of these species were significantly affected by microtopography. So we have Elymus trichicalis, Alaska wild rye, Hordeum jubatum, which is foxtail barley, and Crepus tectorum, which is narrow-leaf hawksbeard, and our only invasive non-native species at the site. So Elymus trichicalis and Crepus tectorum, their occurrence was significantly higher on the ridges than the troughs, whereas the inverse relationship was observed here with foxtail barley. And we were actually able to observe this while we were in the field. So this photo here shows how foxtail barley was consistently establishing within the troughs. We can see how it's creating those linear distribution. And then this next photo here was taken the day after a rain event, so we can see water pooling in the troughs. So these responses to these species to microtopography could influence plant establishment, potentially through water redistribution, reduced exposure, compaction effects, and or seed capture. So finally, the big question of how did our structures influence recolonization? So I want to begin by examining species cover in relation to distance from each structure. So we have our structure names on the top, and then our distances, which I described earlier, here on the bottom. So although the differences here are not statistically significant, we observe clear trends associated with our tallest structures. So our tall snow fence and our Alnus hedgerow. In both cases, species cover increases from immediately in front of the structure to immediately behind, up to 3 times distance. So this pattern suggests that greater structure height may enhance species cover, potentially by modifying microclimate or snow redistribution conditions in ways that favor plant establishment. So we can see that trend there, increasing to decreasing. Now let's explore species diversity and richness. Here, the emerging patterns appear to align more with structure type than with structure height, as we saw with cover. At both snow fences, diversity and richness were lowered directly in front of the fence compared to immediately behind it. Whereas in contrast, at our hedgerows, we see the opposite pattern, with higher diversity and richness immediately behind the structure, or immediately in front of the structure than behind. So although most of these differences are not statistically significant, with the exception of richness for the dryas here, these trends are consistent and suggest an emerging influence of vertical structure on plant community development. I would also like to mention that the absence of significant differences does not imply ecological insignificance. This could have real effects on recolonization in the field. Additionally, the scale of the y-axis on the diversity and richness is very small. We're talking about less than half a species, and this is because our site was very limited in diversity. That could also be why we're just seeing trends here at this stage. So to summarize the main findings and their implications for mine site reclamation, vertical structures did not yet show a significant effect on natural plant recolonization, but these results come from the very early stages of community development. Their influence may become more apparent as the community establishes or hedgerows mature, highlighting the need for long-term monitoring. So lots of potential here with vertical structures. We also found that 3 years post-reclamation, site conditions were strongly driving recolonization, including soil texture, nutrient availability, microtopography, moisture, and temperature. So in general, species richness was higher in moist, nutrient-rich, fine-textured soils. Next is proper overburden handling and storage are essential, as most of the recolonization we saw on site was coming from the existing seed bank. So maintaining viable seed and propagules during storage is critical for natural regeneration. The next is grasses and forbs recolonize rapidly, indicating that the overburden is stabilizing. However, low diversity indicates only partial recovery at this time after 3 years. And the final one is that narrowleaf hawksbeard, Crepus tectorum, was our only non-native invasive species surveyed at the site. And although it is less competitive than perennial clover and alfalfa as observed in southern boreal mine sites, it still may require active intervention to prevent further spread. So again, long-term monitoring. And I think I'm at my time, so I'll just leave it at this acknowledgement slide.
Hello. Is there some questions for Ben? You were very clear. I have a question though. So we've seen on those pictures that the research site is huge. I think it was 1.5 or 2 hectare.
Yeah.
Do you know what's happening currently with Minto metals, leaving the site with Celtic Copper taking over. Is there, with that huge research site, all those plants are still growing? Is there still some data to be collected? Is there still some knowledge to be generated? What do you envision for the future of that research site?
Well, last time we attended the site, we removed our weather station and all of our loggers. So the only materials left on site are the snow fences and planted hedgerows. But to my understanding, everybody that is currently involved in Minto understands the importance of this research experiment. So it has been preserved, and hopefully somebody will be willing to take it on at some point. And yeah.
Thank you. No questions? All good. Thank you, Ben. Thank you very much.